one. What is the equation of load current for a differential amplifier with an active load? What is the definition? This is a direct formula. It's a direct formula. There is no nothing much to think about here. Why? Because we have studied this formula. Current load, we are supposed to find out what is the equation of load current for a differential amplifier with an active load. So see the explanation directly. The load current is given as a product of difference between the input and the output voltage. Load current is given, IL is given as what? It's a product of difference between input voltage and the output voltage, and also a transconductance. So now what is the difference between input voltage and output voltage? The difference between the input voltage and output voltage, I can take it as a VD. It's a difference between the input voltage and output voltage into, it's a transconductance. Transconductance is what? It is given by the GM. It is given by the GM. So ultimately it is nothing else but it is a IL. It is a IL. See, if you want to remember this one, we have studied one circuit in the previous lectures, that this is nothing else but it is a voltage to current converter. It's a voltage. This formula is nothing else but it's a voltage to current converter. Why it is voltage to current converter? Because we have studied in the voltage to current converters, your output, whenever you are having a circuit, okay, I'll tell like this. Whenever you are having a circuit here, it's an voltage to current converter I to V. It is I to, excuse me, it should be V to I. It's not I to V. Why? Because your input is equal to voltage and the output will be current. So it is a V to I converters here. So it is a voltage to current converter. If you are having any voltage to current converter, we have studied this one as a part of university syllabus. Here you are supplying the input as a voltage, and ultimately this is going to be output. And this kind of circuits I have already told you. Any kind of circuit which will be producing the current as output whenever the input is given as a voltage, that kind of circuits is nothing else but I have told that those are called as a transconductance amplifiers. Those are called as a transconductance amplifiers, I have told. And I have even talked about the another circuits in the another lectures. If you can go back to my lectures and you can see, if any of the circuit where current is given as an output and voltage has been produced as an where current is given as an input and voltage has been produced as an output, we call them as an trans impedance or trans resistance. We call them as an trans impedance or trans resistance. But here in this case, what is my question? My question is that whenever an input voltage is given, I'm getting as an output. So now I can say that your output is directly proportional to your input voltage. Your output is directly proportional to your input voltage. What is that proportionality? If I remove the proportionality constant, I'm going to get my output I out is equal to the proportionality constant. What is my proportionality constant? My proportionality constant will be your GM. That's a transconductance. It's a GM times of V in. It's a GM times of V in. See now. What is output current? Output current is what? Your current is always obtained across where? Across a load. Your current will be always obtained across your load, that is IL. So that is IL equal to GM. What is GM? It's a proportionality constant. So it is GM times into the difference of the input and output voltage, that is nothing else but your VD. So this is your formula, how you got this formula from the basics of your transconductance amplifier. So this is your formula which is mentioned over here. It is the difference between the input and output voltage times of the transconductance. So ultimately you will be having this one. IL is equal to GM times of VD. So this is how you got the formula. I out equal to GM into V in, where V in is nothing else but is the difference of the input and output voltage. That is equal to IL equal to GM times of V in. So your answer A is the correct one. Answer A is the correct one. I hope it's clear to you. Is it okay?
Yes, sir.
So the next one, the input voltage of a differential amplifier are the input voltage of differential amplifier means what? The two voltages V1 and V2 they are talking are 2.5 volts and 4.9 volts. If the transconductance is 0.065 mho, inverse of ohm is the mho. Determine the voltage load current entering the next stage. You're supposed to find out the load current which is entering the next stage. It's nothing else but simple formula just now we have seen. IL equal to GM times of the uh, what is this one V. IL equal to GM times of V. Here it is talking about two stages, so it will be combination of two ILs. Since they are talking about the two stages means what? It is a combination of two ILs. So this is a basic formula which you have just now. Apply the basic formula. The current entering the next stages of the amplifier is the sum of the individual load currents. So IL equal to IL1 plus IL2. Since there are two input voltages are given to us, so there are two IL1 plus IL2. Then you can find out what is the formula of IL. IL equal to GM into V in 1 plus GM into V in 2. Substitute the values, you will get the final answer. After substituting, you get the final current IL equal to 0.156 ampere. This is a formula which you are supposed to remember. How come this particular formula has come up? This formula has been derived from this one. The basic formula I out equal to, in fact it's not IL, it's a I out equal to GM times of V in. It's IL equal to GM times of V in. I out equal to IL, that is equal to GM times of your V in. So if you know this formula of your transconductance amplifier or voltage to current for converter circuit, you can easily understand the concepts of your how you got this formula. Okay, so now what's the correct option here? Option A is the correct one. 0.156 is the correct one. This is the correct one. So A is the correct option. Load resistor. RE. RE is neglected for maximizing the load gain in amplifier. Because why we are neglecting the RE? For maximizing the voltage gain in amplifier. Now we are supposed to see. So see, options are requires large chips, requires large power supply, quiescent drop across the RE increases, and all the mentioned above. So see now, what I told, the physical resistor is very large in order to build in a integrated circuit. We know that now presently the integrated circuit size is very small. It's 7 nanometer. Most of the mobile phones nowadays they are going to come up with the 5 nanometer. You can imagine how small is an integrated circuit. If this it becomes very difficult to design the layout or fabricate a resistor over there. So the physical resistors have been removed, and instead of physical resistors they are using the pseudo resistors. Pseudo resistors will be used. So that's why one of the reason, first option is correct one, is which the physical passive elements, any of the physical passive elements, let it be your resistor, let it be your capacitor, let it be your inductor, will always occupy more amount of space on the IC. So that's why they will be neglecting all the passive elements. They will be designing the pseudo kinds of passive elements. Okay, pseudo means which is a false, but it acts as a same functionality of that particular element. So now it requires a larger space. That's the first one. And again, large power supply. Power supply means what? If the larger the resistor, more amount of voltage drop will be there. Voltage drop means what again? That's a power supply also will be more consumed. And again, if RE increases, voltage drop also increases. So all the three are correct options. All the three are correct options. So that's why see the explanation. As the gain is proportional to load resistor, large resistor value is required. In order to have the higher the gain, we know that if gain is more, the efficiency of the amplifier will be more. But we cannot go on. We have stated that gain is directly proportional to your load resistor, but we cannot go on putting the large resistors on the ICs. As the size of IC is very small nowadays, instead of putting the large IC physical resistors on the IC, we can design a pseudo resistor which can produce the same value of the resistance. So that's why the option 4th is the correct one. So that's the reason why we do not use. That's the reason why we do not use the physical resistors over here, because it consumes large amount of space. It requires a large power supply, and voltage drops also will be large. So option 4 is the correct one. Next one. What is the need for level shifter in operational amplifier? Just now we have studied what is the need for level shifter. Level shifter is what? It limits the output voltage. Level shifter means what? It acts as a buffer. The buffer will be transmitting the input to output side in order to limit the output voltage. As the DC level rises stage to stage, which tends to shift operating point. So that's why you are supposed to limit the output swing of the voltage. Output swing has to be between the VCC and minus VEE. The output swing of your signal, ultimately we have studied in the previous classes that the output swing of your operational amplifier, if it is 12 volts means what? If it is 12 volts means what? The positive cycle and the negative cycle we should not be greater than the 12 volts. But practically speaking, we have seen that one. Practically speaking, it should not be the maximum value it can take is only 12 volts only. Here positive side 12 volts and bottom also it can take only minus 12 volts. But practically speaking, it will not even take the 12 volts. It will take what? How much more? It will take 90% of this value only. That's why we have seen that in the laboratories that whenever you try to give some, even though if you increase the input voltage, the output is going to be constant at one particular point. Means what? 90%. Means what? If I am giving a 12 volt, your transistor is going to get saturated at 10.5 volts only. If you are trying to give more than 10.5, output is going to be saturated. So that's why I told your output, the swing of this voltage, practically it will be 90% of the whatever the inputs voltage we supply, or what it will be 90% of the output. It will be 90% of the power supply. You can increase the swing of the output voltage to the 90% of the power supply. Beyond that one, what happens to the amplifier? It enters into the saturation stage. It will enter into the saturation stage. It's approximately, I don't know exactly, somewhere around 10.8. 90% of 12 will be equal to 10.8 or 10.9. Approximately I have written here. So at of 90% only, your transistor is going to be saturated of the total power supply. So answer here, the level shifters are used for what? Limiting the output voltage. For limiting the output voltage. What happens if it's going beyond the 12 volt? Ultimately, malfunction of the device takes place. We cannot give more than 12 volts. If you give more than 12 volts, the malfunction of the device will takes place. Malfunction of the device will takes place. So ultimately, your answer is a level shifter in an operational amplifier is used for what? For limiting the output voltage. For limiting the output voltage. Next one, the limitation of output stage amplifier. What is an output stage amplifier? First of all, immediately you should know the entire, when you see the question, you should know what is that, the diagram of your operation amplifier should come into your mind. Output stage amplifier. What is the output stage amplifier? It is a push-pull amplifier. Output stage, we have studied it. The output stage will be a push-pull amplifier. Push-pull configuration will be used in the output stage. Whereas in the level shifter, it will be an emitter follower. Whereas in the gain stage, it will be a voltage gain will be used there. And if it is a differential amplifier, will be used for the input stage. So its output stage means what? It is a push-pull amplifier. It's a push-pull amplifier. Limitation of an output stage amplifier if it emitter follower with a complementary transistor. What is the emitter? What is the limitation of this output stage? Let us see now here. The limitation of the amplifier is that the output voltage remains 0 until the input voltage succeeds cut-in voltage. This thing you all know. The output voltage remains 0 until the input voltage exceeds cut-in voltage. What is the cut-in voltage? Approximately, see here now, it depends upon the technology again. Depends upon the technology which you are using. We have taken previously the cut-in voltage of your transistor is 0.7 volts. Depends upon technology again. So now we have taken here 0.5 volts. Don't get confused. It is a technology parameter. So now here 0.7 volts. 0.7 volts. What is a 0.7 volts? Is a cut-in voltage. So the limitation of an amplifier is what? until you see you supply some voltage to a transistor. When you supply some voltage to a transistor, all of a sudden the transistor will not turn on. Why? Because transistor requires some amount of voltage to turn on. If you supply from 0 volts, 0, 0 to 0 0.1, 0 to 0 0.3, 0 0.3, 0 0.4, 0 0.5, 0 0.6, until that 0 0.5 or 0 0.6, whatever may be your cut-in voltage, until the cut-in voltage is obtained, your transistor will be completely dead. It is in the cutoff region. So if it is in the cutoff region, the output will be 0. So that's a major limitation. So it's what? Crossover distortion will be happening. Crossover is this kind of situations we call it as a crossover distortions. Crossover distortions will be obtained here. That's a major limitation. So now, an output stage amplifier can produce an output signal when input signal is what? You're supposed to know. An output stage will produce an whenever the input signal is greater than the VBE. Always keep in your mind. Output stage will produce an output voltage. Output stage will produce an output voltage whenever your this one voltage is 2 times the cut-in voltage. Your output voltage is obtained. Your output stage amplifier will produce some output whenever your input this voltage of an output stage is 2 times of the cut-in voltage. 2 times of cut-in voltage is what? 2 times of 0.5 or 2 times of 0.7, depending upon your value. Means it should be as per my value. If my technology of transistor is having a cut-in voltage of 0.5, I'm not finding where is my cursor. Yeah, it's here. If as per my technology, if my VB is equal to 0.5, then 2 times of this one should be what? 1. So you're in an output stage amplifier, due to the crossover distortions, output voltage produces the input voltage should be always greater than the 2 times of a cut-in voltage. Then only your output stage will produce some output. Whenever the input stage becomes 2 times of the cut-in voltage, then only you are going to obtain some output, or else your circuit will be in the process of producing this output. So the option is C is the correct one. Remember the formula, 2 times of the cut-in voltage. Now second, next one, find the disadvantage in the following circuit. We are supposed to find out the disadvantage in the following circuit. There are many options are given, like voltage get attenuated by R1, voltage gets attenuated by R2, voltage gets attenuated by R1 and R2, voltage shift gets increased by drop across R1 and R2. Now let us see now. See now, the option B is the correct one. Why? Because why I'm talking option B is correct one, because your output is taken between the two resistors. Output is taken between the two resistors means what? This output is getting divided. You are supposed to apply the voltage division method again here. You are supposed to apply the voltage division method across this one. You are supposed to apply the voltage division method such a way that it is R2 upon R2 plus R1. It is R2 upon R2 plus R1. R2 plus R1 into R. Into this particular voltage Vin. You're supposed to find out the output here, R1. See now, this voltage, whatever may be the voltage here. So now it is R2 by R1 plus R2 into the voltage here. Means what is happening here? Your voltage is getting attenuated. Your voltage is decreasing. Why it is decreasing? Why? Because the voltage is getting divided in these two resistors. Voltage is not amplifying. Voltage is getting divided into two resistors here. So this voltage is attenuated. So it is attenuated with respect to what? With respect to the R2. Why? Because R1 is directly connected to the emitter. Only the R2 is one which is directly connected to the ground, where the drop of the voltage takes place here. So now the R2 is attenuated with respect to, voltage is will get attenuated with respect to R2. So see now, the output taken at the junction of R1 and R2 increases the voltage shift, but however the disadvantage is that the signal gets attenuated by R2. Why the signal gets attenuated? Why? Because the voltage is dividing here across these two resistors. So that's why I have written R2 by R1 plus R2 into this resistor. The total voltage is nothing else but your R this one, not R V in, it's a V out. It's actually, in fact, it's a V out. So this V out is getting attenuated, it's reduced or it is decreased. Why it is decreased? Why? Because the division of this voltage takes place in these two resistors. So that's why it is a attenuation with respect to R2. So your option B is the correct one. Option B is the correct one. Next one. What is the use of notch and dot in DIP ICs? What is the use of notch and dot in the DIP ICs? We know this one. What is the notch and dot? Why we are using that notch and dot? If I draw this, excuse me, where is my, yeah, I got it. If this is my IC, I'll be having my notch over here. What does this notch tells? Notch tells the beginning of the terminal 1. It will be terminal 1 and last it will be terminal 8 here. Okay, and again you'll be having some other terminals here, null terminals 5, 7, 6, all these terminals will be there here. So what does this notch tells? One small dot will be there. That small dot or is only called as a notch. This notch tells the beginning of the terminals. That's the first terminal, wherever the first terminal starts, you'll be having the notch. So this is your IC. Let me take it as 741 IC, which you have already seen in the laboratories. So now what is the answer? Let us see the correct option. Determine the pin configuration designed to represent device type, represent the property of IC. What is that one? It is used for finding the pin number. To find the pin number. Pin number means what? Your pin starts from the notch only. It's the first pin. So a notch or dot as viewed from top view is used to find the pin number. So the notch is used to find out what my pin number. The terminals are numbered in a counterclockwise. 1, 2, 3, 4. Here again 6, 7, 8. So this is regarding the options. The option D is the correct one to find out the pin number. Next one. In ordering an IC, the device type is represented as. In ordering an IC, the device type is represented as. Your device type will be always an alphanumeric. Remember that one. Your device type will be always an alphanumeric. Why? Because you will be writing as my 741 IC. You'll be writing like this. 741 means what? It is having the alphabets I and C. It is having some numbers. So it's an alphanumeric. It will not be having just alphabet, or it will not be having just numbers or just symbols. It will be having an alphanumeric characteristics. So you can see here all. Micro A 741, LM 741, MC 741, 1741. It's a 741. So these are the different types of 741 which I have written over here. So it's an alphanumeric. Answer D is the correct one. Answer D is the correct one. The major disadvantage of PN-junction isolation technique is. What is the major disadvantage of the PN-junction isolation technique? We have seen that in the PN-junction of a transistor, I have discussed in the class that wherever the two types of junctions have been formed, definitely that will act as a conducting terminal. Whenever the two conducting terminals have been coming in contact, we call them as a capacitor. Okay. So now, whenever the major disadvantage of PN-junction isolation technique is what? Parasitic capacitors have been formed. Parasitic capacitor is what? Unwanted capacitance. It's an unwanted capacitors which are been formed whenever the two conducting plates or two conducting layers comes in contact. So that's why the presence of a parasitic capacitance at an isolation PN junction results in an inevitable capacitor coupling between the component and the substrate. This also limits. What does it limits? Remember this one. It also limits the performance of the circuit at higher frequencies. Why does it limits the performance of circuit at higher frequencies? If the capacitor is large, it takes larger amount of time to charge the capacitor. What do you mean by charging of a capacitor? Charging of a capacitor is nothing else but producing the output. When a capacitor is fully charged, it means that output is obtained. If a capacitor is not charged, then the output is not obtained. So if a capacitor, depending upon this capacitor only, we say whether our output is obtained or not obtained. So that's why this also limits the performance of your this one circuits. So the major disadvantage of this PN junction isolation technique is what? Formation of a parasitic capacitors. So this is a major disadvantage of a PN junction isolation. So option B is the correct one. So thank you here for this lecture.
We are, thank you, sir.
Have you understood my everyone?
Yes, sir.
Is it clear?
Yes, sir.
So today
Thank you, sir.
almost I have covered 20 plus 14 in the previous one. 14 or 12, I don't know. So nearly 35 we have covered today. Tomorrow I hope you have got an exam, right? Day after tomorrow.
Yes, sir. Day after tomorrow.